Today we're going to do galvanic cells and redox potentials, and what that means is we're going to set up our own double cell and see what voltage we can produce using redox reactions. So here is one that I've set up that exactly as you're going to do. So you've got your test tubes, large ones, and you've got here is one cell, so you can see by the blue colour that it's copper sulfate solution. You can see a copper electrode, and you can see that I've clipped on an alligator clip with a lead that goes onto a voltmeter. So we have a circuit because we also have a salt bridge that has been soaked in potassium nitrate solution, and it's just a piece of filter paper and it's draped over, and it's in, you've got to make sure that it's in each solution to complete the circuit. And on this side you have your zinc chloride solution, because this is a Daniel cell. You've got your copper and your zinc. You've got your zinc well away. You've got to make sure the two metal electrodes are not touching the salt bridge. That's the hardest part of this prac. So you have this set up, and then once it's set up, you've got to make sure, just from your own knowledge and from using page 9 of your data booklet, that the more reactive metal is attached to the negative terminal of your voltmeter, because then you're going to get a reading. Otherwise you won't get a reading because you've connected it the wrong way, because this is, the black stands for the negative terminal and the red is for the positive. But you want to be on the finest of the more sensitive of the scales, so you would put it on the 1 volt, not the 10 volt, because they're so small, the voltages that are produced. So that's how you set it up. And what the purpose of this experiment is to build these cells so that you not only can put the metal in order of their reactivity, but you can then work out the electrical potential readings, the voltage, and compare what you get with calculated standard electrode potential voltages that you work out with these this table on page 10. So as you can see in this experiment, you're going to test a number of different combinations of metals. You're going to see which ones produce the biggest voltage, and from that you're going to be able to put all the metals in order of reactivity, with the main aim being to predict the relative oxidizing reducing strength of the 4 metals. And that's what you will do now. So you will set up, and you will also fill in this table. So you will first of all predict what you'll get. And how do you predict it? Well, you actually use these values to work it out. These, really it should say, instead of predicted, theoretical voltage, because these tables were made by people who did it under very standard and careful conditions. And then you're going to work out what you actually got today and put it in there. And we'll get back once you've done it. Alright, so we've done the experiment now, and so I'm just going to show you, this is a diagram of the setup. This is what we did, and you can possibly see it down here as well. Running. The most important part, as was found out, is making sure the salt bridge, which is paper, does not stick to your electrode, and also that everything is in the solution. And when you connect up your voltmeter, you want to make sure your most reactive metal, the anode, is connected to the negative terminal on the voltmeter, and of course the cathode's on the red button of the voltmeter. It does help to have a millivoltmeter, something a little bit more sensitive, because these are very small voltages that you're measuring. This is a result table. If you're not familiar with this shorthand, what this means is it's a galvanic cell with 2 metal electrodes, zinc and copper. You write them so that you have your zinc on the outside, your solid on the outside, a line, then your metal solution, the metal salt only. This double line means the salt bridge, And then the same for the other. So you can see this is a galvanic cell with copper and zinc. This is one with zinc and iron and so on. You put your experimental result in there, which I'm going to ask Samantha to do. The theoretical one here that you've worked out from the data booklet, and then you work out your percentage error. And then you can answer any of the questions in the prac. So Samantha, would you like to come out? Now these will be very different to the theoretical because there is so much error in this prac when you do it in a school laboratory. Don't have the same conditions, the same standards, and therefore very different results. I'll just show you while she's doing that the second part. So you go to your standard electrode potential table on page 10 and you say, okay, the zinc one, you write your half equation. This is for working out the theoretical value. Zinc is being oxidized, zinc solid to zinc ions. That's 2 electrons. This is for the first one. I'm showing you this one. The copper is being reduced. Plus 2 electrons to make copper metal. Oxidation reaction, reduction reaction. This is a reduction table. So that means that you can use the value for the reduction of copper. You must use the right one. There's several. You've got to make sure that it's going 2+ to solid copper. And when you read across on your table, you'll see that the EMF or the E0 value, the standard electrode potential, is plus 0.34 volts. You find the zinc one, it's written as a reduction half reaction. You're going to flip it so it's an oxidation one. When you do that, you change the sign of the voltage to plus. So it becomes plus, what's that say, 0.76. And then when you write your overall ionic net ionic equation by adding these two together, zinc solid plus copper aqueous solution, copper ions, goes to zinc 2+ aqueous plus copper solid. You add these two numbers together and you find you get 1.10 volts. That's the theoretical value there from your data table. So that's what goes in here. And you do the same for each one. That is the homework. You go through and calculate what the theoretical would be and compare yours. This is in amps because it was so low we couldn't get a reading, so we had to use a microammeter. Thank you, Samantha, for putting those in. Percentage error, we'll just do that quickly. Percentage error to calculate, it is always absolute value theoretical minus experimental over theoretical times 100. So let's work out the error for the first one. It would be 1.1 minus 0.09 all over 1.1 times 100. Oh, it's going to be a huge error, isn't it? Oh, not that huge. What is the answer?
Oh, sorry, I wasn't.
I'll just do it quickly. See if you can beat me. It's a huge error. It's a massive error. So 91.8% error. That's terrible. But that's, I would say, to be expected. If you want to do the opposite, you can take that away from 100 to get % accuracy, but the formula for percentage accuracy is experimental over theoretical times 100. So you can see it'd be 0.09 over 1.1 times 100, and you'll get 2% or whatever it is 0.09 divided by 1.1 equals times 100. What do you check me? Well, that's right, 8%. So, did you get 8.2%? 8.2% accuracy. That was quite poor. You can see how they add up to 100, can't you? So, you know, if you wanted to work out your percentage error, then you want to know accuracy, you take the error away from 100% and you get percentage accuracy. And that's it for today.